Okay, so welcome. So let's get started. So this is going to be the second part of the problem session or the tutorial session. I hope to wrap up the problems that I had planned to discuss by today. So from next week onwards, we're going to have the usual classes, and all the details will be shared to you through email. Okay, so fine. Having said that, let's get started. So I'm going to do a slight recap of the problem on geodesics on a surface of revolution, because I think a lot of the things that I said was after the small break that we took, and some of you had left by then or couldn't rejoin after that. So let me do that problem afresh. Maybe I'll go through some of the initial things a bit quickly. Okay, but let me just a second. Okay, so fine. So the first, so I guess we were talking about the surface of revolution, and the surface of revolution, remember, was typically given by two curves, and then you imagine the two curves f and g plotting an actual curve on the R2 plane, and then you rotate this curve with the z-axis as the axis of symmetry. So if you rotate it around the z-axis, then what you get is the surface of revolution. Okay? So the example that we'll be interested in is going to be the curve given by f of v is v and g of v is v squared. So that's basically a parabola, but then you imagine you take a parabola on the xz plane, z is equal to x squared, and then you rotate this parabola along the z-axis. So what you get is a paraboloid. Like it's like a cup kind of shape, but it's a paraboloid. And at the end, the last part of this question, we're going to talk about geodesics on a paraboloid. Okay. But anyway, so given a surface of revolution, I'll recall it for you. So a surface of revolution is parameterized by a local chart. The two parameters are u and v, and the map from uv, which are real parameters, to the surface is given by f of v cosine u, f of v sine u, and the third coordinate, the z coordinate, is g of v. So that means if you fix v, then the height of a point is g of v, and then the u parameter is free once you fix v. So f of v cosine u and f of v sine u, that traces out a circle as u runs through 0 to 2 pi of radius f of v. But this circle is placed at a plane parallel to the xy plane at height g of v, right? That's sort of the structure. So if you take any surface of revolution like we described, if you slice it with any parallel copy of the xy plane, you get a circle. The radius of that circle is f of v. And oftentimes we'll also call it r as a function of u and v, right? So this circle that you obtain by intersecting a surface of revolution with a plane parallel to the xy plane is called a parallel. So that's what this P denotes in this question. Remember, here it says let P be a parallel. So a geodesic is a geodesic. We had a few parts A, B, C of this question, which is also there in the previous slides, talking about what a geodesic on a surface of revolution should satisfy. But a parallel is simply going to be a circle placed at height g of v. Okay. So there are two interesting curves on a surface of revolution. One of them is the family of parallels. So the parallels, as you move up, is going to trace out the surface of revolution. The other ones are geodesics. I mean, the other ones are meridians. Sorry, and the meridians are the ones where you fix your u and you let v vary. So fixing u means you're fixing the angle, and then that simply means it's another rotated copy of the original curve f of v g of v. Right? So f of v is 0 g of v. So that is one copy of the curve when you set u to be equal to 0. So these are the two families of curves, parallels and meridians. Okay, and we have seen already last time that meridians are geodesics, and you can actually go back and have a look at the notes. It's rather easy. So anyway, the question here says you look at a parallel intersecting a geodesic. Let beta be the angle, and there's a terminology here called the oriented angle. I'll talk about that in a minute. Let beta be the oriented angle between the parallel and the geodesic. You have to show that r of t times cosine of beta t is a constant. So where r of t is the radius of the parallel at gamma t, right? So r of t is simply going to be g of v of t, because that is where, sorry, it's going to be f of v of t, because f of v of t is the radius of the circle placed at height g of v of t. All right. So that's the setting. So let me just go forward and show you a picture, because that picture is going to be actually useful. So this is, so if you look at this picture, this is the final question that we'll be solving. But if you think about what we discussed right now and the picture, see, this curve is a circle. This is a specific surface of revolution obtained by the parabola, but this is a parallel P. And this curve that you see, which goes down, turns around, and then goes up, this is it's a curve gamma. This is any curve, but in particular, this is illustrating a geodesic. So the intersection of this curve gamma and the parallel happens at this point. So let's call it gamma of t. And at this point, these two curves have an angle between them, right? This small angle here, that's called beta of t, right? So the reason why the oriented angle is important is because when you're measuring angles between two curves, how do you measure them? Well, you take gamma prime t, eta prime t, you take the dot product, and then you divide out by the lengths. That gives you cosine of beta. However, when you take gamma prime t, eta prime t, you are implicitly using a parameterization of the curve. If you replace the parameterization t by minus t, the direction of the velocity vector reverses. So the cosine is also going to change, and a lot of the angles might change. So you have to fix a parameterization for the parallels and one for gamma, but gamma already comes with a fixed parameterization, let's say unit speed. So in this case, let's say gamma moves up. So the velocity vector is pointing up and slightly to the, in this direction. So for the parallels, for each of the parallels, you have to consistently choose an orientation, and we'll make the convention, or we'll use the convention rather, that each parallel is oriented counterclockwise, which means our parallels are going to go counterclockwise like this. So if I go to the next parallel, I'll use the same orientation for that parallel. I'm not allowed to change the orientation of a subsequent parallel, because the angle beta then changes discontinuously. Okay. So are there any questions with the setup of the? Okay, so that's what it means by an oriented angle, that you fix an orientation of each parallel. If all of them are counterclockwise, then that's it. And that's a convention that we're going to use, okay? So now let's start the question. So a parallel, as we said, is defined by the intersection of the surface with a plane parallel to the xy plane. So it's basically a circle, and it has radius f of v0 square with center 0, 0, gv0. Because remember, gv0 is the height at which the plane is placed. And it intersects at some time t, and the parallel, now you can write down the equation of the parallel, right? So the equation of the parallel is going to be f of vt cosine s, f of vt sine s, g of vt. And remember, this t is that specific t for which v of t is v0. Okay. So for each point on the geodesic, you have the corresponding vt, you look at the height g of vt, you look at the corresponding radius f of vt, and then you take the circle with that radius. So that's the parallel. So what you want is to calculate this quantity, right? This dot product. And that you can calculate very easily. And I'll leave it to you to go back and do a one-line calculation at the back of your notebook. So you remember that gamma prime, just by product rule and chain rule, is essentially given by this. Okay? The gamma prime looks like this, and you also know what p prime should look like, because p is like this. Okay? So you can calculate p prime, you can calculate gamma prime, and we are assuming that gamma is a geodesic of unit speed, let's say, so or a constant speed if you don't want to assume unit speed. But nonetheless, when you calculate, you see that the dot product of p prime with gamma prime is f squared u prime. Okay, everything cancels. Okay, so what is f squared u prime? Well, f squared u prime is what we get by computing, but because of the dot product also equals the length of p prime into the length of gamma prime, correct? Now, what is the length of times cosine of the angle between them? Okay, so r of t is basically the length of p prime. Why? Because p is a circle of radius r of t, and it's it's a unit speed curve there. So well, it's a usual curve on a circle of radius r. So when you differentiate, the velocity has length r. Okay, because I'm choosing cosine s and not normalized cosine. So anyway, you can calculate p prime, the length of p prime s, that is going to be r of t, which is also nothing but g of v of t. Okay, I'm going to use this interchangeably, and gamma prime is what we have, and this is cosine. All right, but you notice that we had two geodesic equations that a geodesic must satisfy, right? Because the internal parameters are u and v for the surface. So you'll get two equations: d2u dt square is equal to something, and d2v dt square is also going to be equal to something else. So if you use the first geodesic equation, and if you integrate that, you can check that f square u prime is essentially a constant. Or put another way, if you differentiate this f square u prime, what you get is the first geodesic equation. Okay, and that is set to be 0, which means f square u prime is constant. So that is another way of thinking about the same thing. So f square u prime is a constant because of the first geodesic equation involving u double prime and some other term. Okay. So that means what? That means this middle term is a constant. The speed of a geodesic is a constant. So whatever they are, this is non-zero, which means r of t into cosine beta t is a constant. All right. So any questions so far? Okay. All right. So okay. So now let's see. So we have already talked about this. So it's a constant. So what does this constant thing gives us? Well, we'll see that this is in some sense one could call it conservation of angular momentum, but I wouldn't go so far as to call it that because, well, I don't personally understand exactly how it is conservation of angular momentum, but perhaps you need to work a little bit more to analyze and get it into a framework where you can call it that. Okay, so most books tend to call it that without giving any sort of reference or explanation why it is that, but it is certainly some sort of a conservative law, or conservation law. Okay, anyway, so now let's quickly do one intermediate question before we go on to the final thing. So the intermediate question actually goes way back to curves and surfaces. Okay, so in curves and surfaces, we have seen that if you have a surface in R3, then a geodesic on the surface is characterized precisely by the fact that the acceleration of that curve gamma. So the characterization is as following: a curve gamma is a geodesic if and only if the acceleration is normal to the surface, which effectively means that the acceleration vector is always going to be perpendicular to the tangent plane of the surface at the point gamma t for all t. All right. So this is a nice interpretation, and actually we did discuss this a little bit in the last, I think, lecture, in the traditional lecture, like before we went on the break. But anyway, so here it's asking you to show that this is also happening for meridians. Okay, so meridians, remember, are specific curves where the u is fixed. So it looks like f of vt, and cosine u is just cosine u0, f of vt sine u0, and g of vt. So instead of proving it for meridians, we'll prove this for all geodesics because the proof is only slightly more complicated, but even that is not too much work. I mean, if you do it for meridians, it will be less work, but there's nothing specific about meridians here. Okay? So yeah, so I mean, this is something we saw just in the previous slide, right? So the velocity of any curve is this. This is simply product rule and chain rule. Okay. So you have f cosine u. So if you differentiate f, it's f prime dv dt cosine u, and then you keep f fixed to differentiate cosine u. So that's a minus sine u du dt. And same thing with the second term. The last term was g of v, so that is g prime. G prime means dg dv, and then dv dt. This is just chain rule. Okay. All right. So if you differentiate with respect to t of the function that we saw just before, we're going to get three components: a of t, b of t, c of t, whatever they are, but it's three components, right? So when you want to say in R3 that the acceleration is perpendicular to a two plane, it's sufficient to check that the acceleration is a multiple of the cross product of a basis of the two plane, right? Because if you take any two basis elements of the two plane, take the cross product, that determines a vector normal to the two plane. And you're saying that the acceleration must be normal, which means it must be a multiple of this normal, correct? This is just basic linear algebra, and the fact that in R3 you have this luxury of cross product. You couldn't have done this elsewhere. So it suffices to show that gamma double prime is a multiple of del u cross del v. Remember, del u, del v are my basis for the tangent spaces. So del u means del by del u, and del v is del by del v, correct? And so these span the tangent space at any point. The cross product is going to be normal, and that's what we aim to show. All right. So any questions so far? Okay. All right. Okay. All right. I'll leave this to you to check again. So see, I'm the ones marked in red, as you might have inferred by now on the slides, are official exercises. Okay, so I might, if I have the time, I might compile all of them and send you a separate file. But as it is, I think creating slides and adding things is taking enough time. So the point is, the color codes are such that there are some remarks which are in different colors. The usual ones are black, and then the red ones are exercises. The ones which are starred, you can leave them for now, but the ones which are regulars unstarred, those are actual exercises. So you should ideally try them, because this is part of the official coursework. Okay. So we have to show that A of t looks like this and B of t looks like this. I'll tell you what alpha is in a moment, but just bear with me. So you might be confused saying, why should I write A of t in this form? Fg prime alpha over Fg prime. Why didn't I cancel Fg prime? Well, you'll see the reason for this, because remember, we are trying to get a scalar multiple of del u cross del v, and del u cross del v has a specific form. So that's the reason for writing A and B in this form. Okay. Okay. So what about C of t? Well, C of t, you have to differentiate the earlier one, which is g prime dv dt, right? So if you calculate C of t, so this was what you get. Okay. So anyway, so if you calculate C of t, we'll start off with this. Okay. Actually, the point is I'm dividing by g primes. Even here, you might say there's a g prime in the denominator, there's a g prime up here, and there's g prime square up here. Well, you could have cancelled g prime, but I would like to leave it this way, because even if you cancel, what do you get? You get g prime v double prime plus g double prime v prime square. Right? But that's it. So that's what you get just by product rule and chain rule. So that's it. But now you can replace v double prime using the second of the two geodesic equations with this quantity. Okay, so that's what I'm doing, because remember, the second of the two geodesic equations looks like d2v dt2 plus some other terms. Right? So that's what I'm doing. So you simplify, and you can also make use of what is u prime at some point. So again, I'll leave all of that for you to check. But at the end, when you simplify all of this, this is what you get. And from this, you can infer what alpha is going to be. And this is, again, a simple thing. You just have to sit down, look at the slide for maybe not even 30 seconds, and you'll infer what alpha is. So this is the same alpha that appears earlier here and here. Okay. So the point is, this is a simple routine computation. Given two vectors, you calculate the cross product. On the other hand, you can simply calculate second, derivatives of some curve in R3. So this is what you get. So it looks like alpha over fg prime is the common scalar in all the three quantities, right? So if you remove alpha over fg prime from A, from B, and from C, what are you left with? You're left with fg prime cosine u, fg prime sine u, minus f prime. So at this point, we'd be done if you could show that del u cross del v is fg prime cosine u, fg prime sine u, and minus f prime, correct? And the constant c, the scalar c, is going to be alpha over fg prime, and hence it will be normal. So that's what we're going to, now we're going to compute the cross product. Okay. So is everybody okay so far? All right. So, so at this point, if you calculate del by del u and del by del v, well, we had written out del u and del v earlier. You'll see that that's even simpler than this calculation. It's precisely going to be what I just said: fg prime cosine u, fg prime sine u, minus ff prime, and that implies that the acceleration is normal to the tangent plane. And by this basic result of curves and surfaces, such a curve is a geodesic, okay? Or a geodesic also satisfies this. That's the Economy criteria. So that takes care of the last part of the problem, okay? All right, so, okay, so now let's come to the actual question that I am personally interested in. So, so it says that you look at a geodesic, which is not a meridian. We know that meridians are geodesics, and meridians on a parabola are not very interesting. They're simply the curve z is equal to x square, and then if you rotate it along the z-axis, you get all the meridians. But those are not very interesting. So you choose a geodesic which is not a meridian, okay? And you have to show that it intersects itself infinitely many often, okay? So this is the picture which you saw earlier, but I'll show it once more. So this is a picture from Ducarmo's book. And so this is what a paraboloid looks like. And what he's drawing here with this curve is a prototypical geodesic. So it sort of comes down, goes around, and then it goes up. But you see, this has a tendency to sort of, this part of the curve has a tendency to go up and then go around counterclockwise, go up and go around counterclockwise, like a spiral. And it's same with this one. This has a tendency to go clockwise and go up, go clockwise and go up. So if this is the expected behavior, then this phenomena seems to suggest that, yes, indeed, a geodesic which is not a meridian should intersect itself infinitely often, because it has two strands, and as t goes to infinity on one strand and t goes to minus infinity on the other, because you see, here if I say go up, that is going reverse in time. They seem to be going in opposite directions, but they're spiraling infinitely many times around the z-axis, so they must intersect by intermediate value theorem, okay? And that is precisely what we're going to show. So this is actually precisely the picture that you should have in mind. This is not just a picture that you draw for convenience. Okay, so anyway, this hints at the result, and this is precisely what we're going to do. Okay, so is the picture clear? I can explain the picture once more if people have any questions. So the parallel at this point is not very important, but this is the typical phenomenon that this strand is going to go up and go counterclockwise, go up and go counterclockwise, and this strand is going to go clockwise, go up, go clockwise, go up. So in particular, this suggests a few things, right? If it is just winding around and around and around, that seems to suggest that this angular parameter u, remember u is the one which tells you how the angular parameter on a circle if you intersect it. So this parameter u seems to be monotone, because it seems like the hands of a clock. It's just going around clockwise all the time, infinitely many often. So that seems to suggest, first of all, that u is monotone. On the other hand, you see that the radius, if the curves actually go up and keep moving up on either ends, the radius of an associated point. So if your point is here, the radius is this distance, right? And this distance is what? This distance is basically r of t. But as your point moves upward, this distance actually increases. So that seems to suggest another thing, that r of t actually goes to infinity as t goes to plus infinity as well as minus infinity, because it happens also for this strand, okay? So that seems to suggest two things, that u is monotone, u of t, and r of t, which is also going to be our v of t, because remember r was what? It was the radius, but as I said, r is f of v. So r of t at time t is nothing but f of v of t. But what is f? F is given to be just the identity function. F of v is v. So f of v of t is v of t. So I might interchangeably use v of t instead of r of t, or r of t instead of v of t, and hopefully there is no confusion when it appears. Okay. So that seems to suggest that if the curve really goes up after a certain point on both ends, r of t should go to infinity as t goes to plus minus infinity, right? Okay. So let's see what happens. and that's expected to happen. So as the geodesic is not a meridian, u prime t is never 0. Okay, why? Because if u prime t is 0, that seems to suggest that there's no change in the angle, and that means that the tangent gamma prime, or the velocity gamma prime at t, if u prime t was 0 at some point, is going to be entirely vertical. Okay, but that would mean that the geodesic gamma has to be a meridian, because the meridian is a geodesic which has, like vertical tangent vectors or vertical velocities, so to speak. And the uniqueness of geodesic tells me that if I give you an initial point and an initial velocity vector, there's a unique geodesic. So u prime t is never 0. That's the argument, because if u prime t is 0, then the velocity points up, and there are no, there's going to be some contribution along whichever axis it is, but it's not going to have any contribution sideways. That's the point. Okay. So u prime t is never 0. So what does that tell us? So that tells us that u prime t is either entirely positive or entirely negative, right? But remember, we're talking about a curve defined on R, let's say, okay? And I'll address this issue in a moment, but let's assume for now that the geodesic is defined for all times. So R is a path connected set, u prime is a continuous map, u prime is never 0. So that implies that the image of u prime is path connected, so u prime is entirely positive or entirely negative. In either case, u is monotone, correct? So there's a typo here, this should be u, okay? So u is a monotone function, either increasing or decreasing. So what you could do is you could say, I'll just switch t with minus t to make u prime, u increasing, for example. You could do that, and we'll do that later on anyway. So that takes care of the first bit. So this is a typo, just make note of it. U is a monotone function. So what we are left to show is that gamma winds around the z-axis infinitely many times. Okay. So why is that? So see, u being monotone does not mean that ut goes to infinity or ut goes to minus infinity, right? So we have to do some estimates to show that u actually goes to infinity. But remember, u is the angle, but as a parameter, it's going to infinity. But when I think of u in the surface, it's cosine u and sine u. So if ut goes to infinity, cosine and sine, they trace out the circle infinitely many times, because the circle has period 2 pi. Right? So that's the infinitely many winding around statement. All right. So how do you show that? So this is our aim, that ut goes to infinity or ut goes to minus infinity as t goes to infinity. And replacing t with minus t can always ensure that this happens, okay, as I said. So, okay. So let's start with what we have. So we know that it's a unit speed geodesic. So the length of the velocity vector is 1, or the speed is 1. But you know what the speed is. If you calculate, and this is something we did calculate last time, the speed is simply this, okay? It's 1 plus 4v square, v prime square, plus v square, u prime square, okay? So, okay, so this is now simple. You can remove v square u prime square, that's a positive term, and you still have bigger than or equal to square root 1 plus 4v square v prime. That is bigger than this. That is just AMGM inequality, which is bigger than v square prime, right? Okay. So at this point, you can integrate this inequality. What do you get? You get 1 is bigger than or equal to, if you integrate this, what you get is this. Okay, this is again something straightforward, that you get v square at t minus v square at 0. Absolute is less than or equal to the integral from 0 to t, this thing above. But that is bounded by 1. So if you integrate 1 from 0 to t, what you get is t. Right? So you get vt square minus v0 square, the absolute, is less than or equal to t. Okay? Are there any questions? Okay, so allow me to maybe move on to the next slide. So, okay, so this basically tells, remember, whenever you have a minus b absolute is less than or equal to t, and we're talking about t positive, okay? We are going to do the t negative in a similar fashion. So t positive, which means this is less than or equal to t, okay? That's pretty immediate. So at this point, I'll ask you to show again a couple of lines computation, that cosine of beta t can be written also as u prime t vt. Okay. So this is essentially a reformulation of Clairaut's formula. This formula that we proved, r cosine beta is a constant. As I said, there is some sort of a conservation law that is called Clairaut's law or Clairaut's formula, and this is a reformulation of that, if you wish. So this is something you should just go back and check. It's pretty easy. Okay. So anyway, so if you use either this version or the original Clairaut's relation, you'll see that. See, this thing tells you what, that you can remember r is the same as v, which we just discussed. R of t is the same as v of t because our function f of v is v, which means I can multiply by r of t here and I get u prime r square, but r times cosine beta is constant, so u prime is simply constant by r square, right? So I simply multiply by v here, and then this is v square, and I move it back here, but v cosine beta is constant, so u prime is c over r square or v square, and then I take absolute. So this is essentially Clairaut's law. But then I can use this inequality up here, and r and v are the same, I repeat. So this is bigger than or equal to this, okay? And then we're done, right? So why are we done? Because now it's a matter of integrating u prime t, the absolute. And if you integrate, you're going to integrate 0 to infinity dt over r0 square plus t. And this evidently goes to infinity, okay? Because of how you integrate this thing. So that tells me what? That tells me that, so I have absolute value of a function f prime, and I'm integrating that from 0 to infinity, and that goes to infinity, okay? So that actually tells me that ut actually has to go to either plus infinity or minus infinity, because I'm taking absolute here. Otherwise, it would say that ut goes to plus infinity, right? This is just fundamental theorem. And you can similarly prove it for negative t. So the point being that u is monotone, and this argument shows that either ut goes to plus infinity and u of minus t goes to, ut goes to plus infinity as t goes to infinity, and ut goes to minus infinity as t goes to minus infinity. So at both ends, they go to the corresponding ends. T goes to plus infinity implies ut goes to plus infinity, and so on. Or there's a switch. Okay, but you can always replace that by replacing t with minus t. So at the end, we may assume by replacing the parameter t with minus t that this happens respectively, meaning as t goes to plus minus infinity, ut also goes to plus minus infinity. All right. So I'll just maybe pause here for a moment, just to wait to see if people have questions. Okay. So this is not too hard a computation, but you sort of have to put things in the right place and then things fall out. And the only last thing we're doing is something synthetic. We're saying replace t by minus t to ensure that the limits go to the corresponding limits rather than switching over. That's all. So that's just changing the orientation of the curve, if you wish, replacing t by minus t. So are there any questions or comments? Okay, so all right, so then let's move on, and we'll also assume that c is bigger than 0, and this is because you can show actually that this happens. So remember, what is c? So this c is the constant that appears up here, right? So this is r of t cosine beta t is c. So what happens when c is 0? If c is 0, that means r of t into cosine of beta t is 0. So r of t typically is not going to be 0 because r is the radius of the circle on which the point gamma t lies, correct? And unless the curve is a constant, r of t is never 0, which means cosine beta t has to be 0. But that simply means beta t takes the value pi over 2 or minus pi over 2. And it's continuous, so it takes one of these values as a constant. But when beta t is pi over 2 or minus pi over 2, what does it mean? It means that the curve gamma intersects the circle at 90 degrees. But the circle is itself a horizontal curve, and anything which is intersecting at 90 degrees means that the curve gamma has to be a meridian. But we are assuming that the geodesic is not a meridian. So because of that, c cannot be 0. Because if c was 0, then the curve should become a meridian, but we are not in that case. So either C is positive or negative. So that's forced on you. Okay. Now, if C is positive, that means what? R is already positive. It's a radius. Cosine of beta has to be positive, which means cosine of beta has to be between minus pi over 2 and pi over 2. It cannot be pi over 2 or minus pi over 2, and it cannot be more than that because then cosine becomes negative. Correct? So that's all. Okay, so this is this is going to help us because if you choose C to be negative, the same analysis applies. Okay. So yeah, so this is the remark that I said. If C is 0, then gamma is a meridian. So let me just pause here for a moment. I think there's some. Can people still hear me?
Yes, sir.
Okay. No, because there was some issues with the internet. So okay.
So the audio was lost for a few seconds before this.
Oh, in the previous slide here.
At the end of the previous slide,
So
yeah, this red comment till this we had. Beyond that, we couldn't hear. I couldn't hear.
So the red line we discussed show that C bigger than 0, or you want me to go over that?
So till that it was fine.
Including that exercise.
No, not the exercise.
Okay. Yeah. So the exercise I'm saying is that C cannot be 0 because C 0 implies it's a meridian, because then beta has to be constant pi over 2 or minus pi over 2, but it's the angle that the geodesic makes with a horizontal circle. That means the curve has to be it's a vertical tangent vector, so the curve has to be a geodesic. It has to be a meridian. So now I'm saying either C is positive or negative. It's a constant. So C bigger than 0 means what? If you go back here, R cosine beta is constant. And this is positive. R evidently is positive. It's a radius. So cosine beta has to be positive. But then you see that the values of beta can only be from minus pi over 2 to pi over 2 in that open interval, or from pi over 2 to 3 pi over 2 in that open interval. It cannot be minus pi over 2 or pi over 2. Right? But cosine is positive means beta has to be in this interval. That's all. Okay. So is that okay?
Yes, thank you, sir.
Okay. So yeah, so then as I said, it's not a meridian. So if C is less than 0, you can orient our parallels clockwise, and then so the point is you just change the orientation of all the parallels, and C changes to minus C because you're simply going to switch from beta to pi minus beta or something. So the cosine changes sign. So it's not a big deal. We assume C is bigger than 0. So now let's come to the main claim that R of t goes to infinity at both ends. Okay. So all right. So just a second. Okay. No, somebody said something on the chat. Okay. So as gamma has unit speed, we write down the unit speed fact again. So 1 is equal to 1 plus 4r squared. Now remember, I have replaced v with r, and I've said this many times. R is the same as v because f of v is v. So this is what you get. 1 is equal to this quantity, right? But what is u prime? Remember, we use this. It's a variant of the Clairaut's formula. U prime is c over r squared. So u prime square is c square over r to the 4. And there's a r square already in place in the numerator. So this simplifies to c square over r square. Correct? Okay. So what do we obtain? So you simplify all of this, you see that this is what you get. R prime square, and this is a very simple simplification. R prime whole square is r square minus c square divided by 1 plus 4r square. Okay. So at this point, you might say, okay, can we solve this equation? And that would be nice. And we'll actually make a digression a bit later in the discussion and actually say how to solve this explicitly. And but just hold on to your patience until then, okay? Because at this point we don't need to solve them. We just need to check some asymptotics. So the first thing you note is that if the angle beta is bigger than 0 for some t0, then what happens? Then I'm claiming that beta is bigger than 0 for t sufficiently close to t0. Well, that's because of continuity of beta, right? Because beta is a continuous function. So if it's positive at t0, it's positive for t sufficiently close. If I take square roots, what do I get? I get r prime. And remember, what is c square? C square is r square cosine square beta. So if I subtract this becomes r square sine square beta. And sine beta is positive in that neighborhood. So when I take square root, this is what I get, correct? R prime is r sine beta divided by square root of 1 plus 4r square. But this is evidently positive. Okay, this is positive in this specific interval around t0. So in particular, this means r prime is bigger than 0 because I can cancel off the r and I get r prime as a positive number. Okay. So that says what? That says that. Okay. So let's go on there. So r prime is bigger than 0 at t0 in particular. So r is increasing at t0. But if r is increasing at t0, what can you say about beta? Remember, r cosine beta is a constant. And if r is increasing, then cosine beta should be decreasing, correct? And our beta is basically from minus pi over 2 to pi over 2, correct? And we're assuming that the angle beta is actually positive, which means it's actually between 0 and pi over 2. Remember, we said that c bigger than 0, to go back, remember we said that c bigger than 0 means beta lies in this region. But now we're saying that we're choosing a t0 so that beta of t0 is actually positive, correct? Like here. And for t sufficiently close to t0, that simply means that beta on that interval is between 0 and pi over 2. So on the interval 0 and pi over 2, cosine should decrease because r is increasing at t0. And that means r times cosine is a constant, which implies cosine of beta should be decreasing, but cosine of beta decreases as t increases, right? So the point is beta is also increasing at t0, and hence sine beta is also increasing, because this is the only way that cosine can decrease, because r times cosine is a constant and r is increasing, so cosine is decreasing. So the angle beta is increasing at t0, so sine beta is also increasing at t0. All right. So it's a very simple argument, but it's kind of nice to see how things fit together. All right. So, and you can iterate this process at the next stage. For example, choose a point sufficiently close to t0 and iterate this process. So the upshot is that because you could have taken the positive square root out and so on, that r is actually increasing on this whole interval, t0 through infinity. It may not go to infinity, but it's increasing. Okay, so we are left to show that r actually goes to infinity. So I'll pause again for a moment because maybe there's some audio issues. Is everybody okay with my voice, or people are having issues hearing me? Somebody has dropped off, I guess, but okay. Okay, fine. So can I continue? Okay. So if there's no objections, let's go on. So this is what we want to show, that r of t goes to infinity as t goes to infinity. All right. So, well, if it is, we are done. If not, assume that the limit exists, okay? Because it's increasing anyway. So assume that the limit exists, and let's say the limit is r infinity. Okay, so what do we do with this? Well, again, you look at the unit speed equation. What does the unit speed equation tells you? The unit speed equation tells you that r prime square, remember this is the equation that we are obtained, right? This is the equation, correct? So if r of t as t goes to infinity had a limit, you could simply plug in the limit here, correct? Because this right hand side would have a limit, this would have a limit. So let's see what we get. That's all I'm doing. So let's plug it in there. We get limit r prime t whole square, t goes to infinity. So this is r prime t whole square because of the very nature of things, right? So this is okay. So this should really be r square prime whole square, but let me just go on here. So there's a small, just a second, there's a small typo here, I think. So no. So all I did is I removed the r square from here and I moved it down here. So this equation also looks like r prime square is equal to the same numerator divided by the same denominator, but then you pull this r square from here and put it down here, okay? So all I've done is that. So if I do that, and then I simply take the limit, what do I get? I get limit of this quantity square is this, okay? And this is evidently bigger than 0. Why? It's bigger than 0 because remember C is, so if you think of C is R of t cosine beta, and R of t goes to R infinity square, and beta will go to something, right? But remember, beta is always increasing as an angle, and beta of t0 is always bigger than 0, right? So the only limit that it can go to is pi. Okay. So yeah. So anyway, so sorry, the only limit it cannot go to is pi. But what I wanted to say was something else. So there was something that I wanted to say. So I misspoke here. So I'm claiming that this limit is positive by saying that this denominator is positive. Okay, so that's something you just have to check from these limit conditions that we have. But the upshot of all of this is r prime t, this derivative has a limit, and the limit is actually in fact positive because it's going to be square root of this thing. Okay. So what does it mean? You have a curve r, you know that it's increasing as t goes to infinity. It's actually increasing on t0 infinity, and you're saying that the derivative of that actually has a limit as t goes to infinity, and the derivative is actually positive. The limit of r prime t is positive, but that in fact means that r itself should go to infinity. That's a contradiction, right? If this is, that cannot happen. Okay. So the point being, you cannot have a finite limit of this r, because if it was, then r prime t would actually have a limit which is positive, but that would mean that r actually has to go to infinity, which contradicts the very assumption that the limit is finite. Okay. So you can do a, so what's left to do? Well, we started off with the assumption that beta is bigger than 0 at some point t0. Okay. So that it's increasing and so on. So what if this is not true? So this was the assumption, right? If I go back, this was the assumption. If beta t is bigger than 0, then all of these happen. What if that's not true? Well, if that's not true, that means beta t has to be less than or equal to 0 for all t. But then you can show that the limit of r prime t is going to be 0. Okay. But r prime t, on the other hand, is also going to be bigger than 0 for t large enough. And here you have to use the second of the two geodesic equations. So remember, the second equation talks about d2v, dt2, and so on. So here our v is r. So that is saying r double prime plus minus some terms is 0. So from that, you can deduce that the velocity has to be positive for t large enough. On the other hand, if this was true, you can deduce that the velocity will be 0 as t goes to infinity, and that's an evident contradiction. So this is saying that you cannot have this phenomenon, okay? Which means whatever we assumed first is the phenomena that actually happens every time. Okay, that there's some t0 for which beta of t0 is positive. Okay. So now you can apply the same argument by replacing t with minus t, and you can show that r of t goes to infinity when t goes to minus infinity. So this is the analytic, the analytical part of the argument. But remember, what does it say in terms of geometry? It's saying, remember, that r of t is the radius, and this is saying, if you think of the curve as t goes to infinity winds around, say, counterclockwise infinitely many often, and it also moves up. That's what r of t equal to infinity means. Okay. Similarly, as the curve winds around the z-axis as t goes to minus infinity, it also moves up. That's what this equation is saying. So it's like this DNA kind of helix. They have two spirals, they're sort of moving up, but they're opposite oriented. And so by intermediate value theorem, they must intersect infinitely many often, because if they intersect once, then you look for all t bigger than that on both strands. And since they're traversing this surface of revolution in opposite directions, and they're also moving up, they should intersect once more at some other point. And then you remove that intersection, look for all t bigger than that, and you iterate this process, and it is going to intersect infinitely many often just because of this phenomenon. So it's somehow very rigid, that the curve actually might go down and do some spiral at the base of the paraboloid, but then once it starts moving up on both ends. That's the picture that you should have in your mind. Okay. So, are there any questions with this? I mean, I seriously urge all of you to maybe go back and have a look at this calculation and see if you have any questions here. It's not too hard, but then you have to put all the small things together and just check some of the things I left as an exercise. But this is sort of the gist of it. Okay. So, any questions? Okay, so let me go on to make a remark regarding what exactly is a geodesic. Can we characterize them by an exact equation? And can we say something more? So this turns out that this is actually a theorem, or so there's a small typo here, there's an R missing. It's going to be a theorem published in the Bulletins of AMS 1941 by Ling and Recht. So they actually precisely talk about geodesics on this specific surface we have been talking about. Okay. So the assumption that a non-meridional geodesic exists for all. So we assume that the geodesic is defined for all t, right? All times in R. So we didn't quite care to justify why that is so. Why not the geodesic defined for a small time? So the point is, due to Hopf-Renoir theorem, a manifold, a Riemannian manifold is geodesically complete if and only if it's topologically complete. Okay, and there's other criteria, but this is sort of one of the two equivalent criteria. So remember, a paraboloid is a complete metric space as a subset of R3, and by Hopf-Renoir it is going to be geodesically complete. What that means is that if you have a geodesic defined on the paraboloid, it's going to be defined for all times. Hence, we could have made that assumption of assuming that the geodesic is defined on R, all of R. Okay. So that's the remark. Okay. So now this is more like I couldn't think of a better name, so I called it an advanced remark. I don't know what else to call it. So we'll point out an analysis of the problem by Ling and Recht. So I gave you the reference here. It's a short paper actually, 4 pages maybe. If you want, you can even read it up. So what you could show, I mean, they show this, but you could show this as well. Remember, you have du dt and dv dt, and v is my R here, so I'm not going to talk about v anymore. I'm going to switch to R entirely. So you have du dt and dv dt, and you can combine them to talk about du dv. Okay, and if you combine them, this is one of the first things you can deduce. This is just immediate from du dt and dv dt. That du dv looks like this quantity. Okay. All right, so fine, we get this. So why is this useful? Well, so as I said, this can be deduced from Clairaut's law and the fact that geodesics have unit speed. So it's not something substantial for a paper. So what did they do? So they found an explicit solution for a geodesic, of course for C non-zero, because we don't care about meridional geodesics, for a geodesic passing through U0 R0. Okay. So this is what they get. So this is as explicit as solutions of differential equations get. I mean, it couldn't be any more explicit. So there's the U0 initial term, there's tan inverse, there are two terms, and there's some log terms, and the C comes in, the C from Clairaut's formula. So that's what, okay? So you can check that it satisfies the initial conditions, and you can check that this is a geodesic, okay? But this is a geodesic defining U in terms of R, which are both functions of T. Okay, so you can see from here, I mean, okay, it might not be too easy to see, but anyway, so they do prove that R cannot be bounded, but we did prove R is unbounded, it actually goes to infinity, but even from here you can show that R cannot be bounded because U is monotone. Okay, but what they show is actually something more interesting. They show that if as R goes to the parameter absolute C, so remember here you can let R go to absolute C, then U will have a limit. It will be U plus whatever limits happens here, and whatever limit happens here as R goes to absolute C. We call that U bar. So you will have a limit U bar as R goes to absolute C. So what they do is you look at the image point the image of the point, the image of the point C bar, absolute C and U bar. So along with the Z axis, this determines the plane which will divide the geodesic into two conjugate rays. So what do I mean by conjugate rays? By conjugate rays, I mean there'll be one ray and the other one is going to be sort of reflected across this plane. And if you know one of these rays and how it traverses, then you know the other half of the ray, because that's going to be essentially moving in the other opposite direction but a mirror image. That's what conjugate rays means. Okay? So that's also justifying our assumption that R of t goes to plus infinity and R of t goes to plus infinity on both ends of t, because even for our geodesic, there's going to be a point through which a plane through which if you cut the geodesic, the plane is going to contain the z-axis and contain some other point, and this is the point. So that if you cut the geodesic along that plane, you're going to get two parts of the geodesic, one ray on one side and one ray on the other side, and sort of that's well, technically you shouldn't get two parts because the geodesic winds up, but just pretend that you slice it there and then one of them just goes up and clockwise and the other one goes up and counterclockwise, but they're conjugate through this reflection principle. Okay, but they explicitly provide what are the double points, and they do more analysis with this. Okay, so with this explicit formula, so they actually tell you when the double points are going to occur, at what distance, and they separate them out into bands so that you have double points and then there are no double points in the next band and then you have a double point. It's very explicit. It's a short paper for those who like computations or may find these kind of things interesting. But again, this is an advanced remark because this is not something too relevant for the course, right? So, okay, so now you have two more problems. So I want to discuss the exponential map for S2, and I want to discuss, let's see, the last one is about, I forgot, last one is about something else. Okay, let's see what happens. So we'll see. Okay. So are there any questions so far on the general things we have been discussing, or any issues regarding the internet? Can people hear me? All right. I think some people have left, maybe one or two people left, but anyway, hopefully they'll join back in later on. Okay, all right. So now we are back to some slightly more mundane questions. I mean, not too mundane, they're interesting on their own right, but slightly less computations compared to what we just did. So it says compute the exponential map for the sphere. And the Riemannian metric that you have is the round metric induced from the Euclidean 3 space. Okay. All right. So we already know what to expect, right? We know from studying the globe, atlases, looking at the world map and so on, that the geodesics are great circles because planes tend to travel along great circles to minimize various things. So we know that geodesics are to be great circles passing through, in this case, the North Pole, because the exponential map is initialized at 0, 0, 1. So the exponential map should take a tangent vector at 0, 0, 1 and take a geodesic, which will now be a great circle with that tangent vector as the initial velocity, and it's initialized at 0, 0, 1. So it's going to be a great circle which starts at 0, 0, 1 and tends to flow down to the sink, which is the South Pole. 0, 0, minus 1, right? Okay, but let's see why we get that. So for that, it's best to work with a chart so that we can pull everything back to a coordinate in R2 and then work everything out there. And part of this was done in the class. So remember, we have the stereographic projection from the South Pole, which will be a chart around 0, 0, 1. So what is this map? This map is x, y, z goes to x over 1 plus z, y over 1 plus z, and 0. And one way to check that this is the correct map, not 1 minus z and 1 minus z, is because when z is minus 1, this goes to infinity, right? So that's a good way of checking that if you remember most of the formulas correctly, it's a good way of checking whether the signs are correct and so on. So what is the inverse map? Well, this is also something that we talked about. The inverse map is given by 2x over x squared plus y squared plus 1 and 2y over r squared plus 1 and 1 minus r squared over r squared plus 1. Right? Okay, so fine. So what do we want to do? Well, remember we want to take the tangent vectors here, which is del by del x and del by del y, map it to two tangent vectors here, compute their inner product coming from the round metric, meaning compute the inner product pretending that this is in R3, and that's going to give us the pullback Riemannian metric on the chart, and we're going to solve for geodesics on this chart, because then applying the map psi back, we're going to get all the geodesics. All right, that's the goal. So you work on a chart, you write down the Riemannian metric locally in local coordinates, and then you solve for geodesics there by solving for the Christoffel symbols, and then you use the chart to map the geodesics in the local chart to geodesics in the manifold. That's what you do. Okay, so the first exercise, and this is something we have done in class, that you calculate the linearization of this map at the point xy. So the del by del x vector goes to this vector. Okay, so this is the tangent vector at the point psi of xy. And one way to check that this is correct is that this thing should now be perpendicular to psi of xy, because any tangent vector at a point P on the sphere is perpendicular to the point P, correct? So that's something you should be able to check. So is it clear? So this is a quick recap of things. So we have all seen stereographic projection, we've all seen the inverse. I'm just doing it for the south pole because that will give me a chart for the north pole. All right. Okay. So the same proof implies that, well, you just replace x with y practically and interchange coordinates. So the same thing is going to work out. If you do the first exercise, this is almost for free. All right. So now what do we do? Well, so now in particular, we deduce that the Riemannian metric is this. So why is that? Well, remember, you have to, how do you calculate the Riemannian metric? Well, you have to take this vector, take the inner product of this vector with itself in R3, which means you have to take two copies of this vector, take the dot product, and use the fact that, you know, certain things will sum to 1 and so on. So that's again something we did, but if you haven't done the exercise when it was done, you should go back and check it. So this is this quantity, because this quantity is simply the length square of this quantity. This lower diagonal entry is 4 over this. Okay, and this quantity is nothing but the length square of this. Similarly, the length square of this is going to be 4 over r square plus 1 whole square. And it should be clear from how things are defined that this vector is perpendicular to the corresponding vector for d by dx. That contributes 0 in the off diagonal terms. Okay? So this is the Riemannian metric, and I'll move on because this is something we did spend part of a lecture on. So this is the Riemannian metric. So what are the geodesics of this Riemannian metric? Okay. So let's calculate the Christoffel symbols. So what do you get? Well, remember the Christoffel symbols will have all these del I, g, j, k, but the off diagonal g, j, k's are 0. So the only things that's going to appear here are del 1 of g11 or del 2 of g11 and del 1 of g22 or del 2 of g22. No g12s can appear because they're 0. Similarly, this is the inverse matrix of G, and the 1 1 means it's the 1 1 at the entry of G inverse. So since G is diagonal, G inverse is also diagonal, which means G upper 1 2 is 0, right? So anyway, this is something you can calculate, and I calculated one of them for you, but I'll leave it to you as an exercise to check that this is what you get. Okay. So, but before I move on, is everything clear so far? Any questions or comments? Okay, so let me go on. So anyway, this is something you can just take a piece of paper and then do. This is not any hard because this is a very simple matrix. So the point is, now we want to solve for a geodesic initialized at the origin, because we want the exponential map in this case to be the images of the geodesics at the origin of the chart under the map psi, and the origin goes to the point 001 under the map psi, right? Okay, and with velocity, let's say cosine theta, sine theta, okay, because we want the speed to be 1. So we can try this. So on the plane, you do not have the standard metric. You have the Riemannian metric 4 over r square plus 1 whole square times identity. And you're trying to solve for geodesics there. So if it was the standard metric, you would expect that the radial lines are geodesics, right? But the radial line with slope theta is given by t cosine theta, t sine theta, right? So the curve gamma t, if you are on R2 with the standard Euclidean metric, would be given by t cosine theta, t sine theta. However, this is not the standard Euclidean metric. So t might not be the right parameter to look at. So instead we try r of t cosine theta, r of t sine theta, because r of t cannot be linear, because the metric, the change of the metric is I mean, it's changing with r square and it's not constant for sure. So that's the reason for trying this, okay? So if you want to try out some function r of t instead of t, because t doesn't work, then you'll have to solve the geodesic equation with the Christoffel symbols that we just discussed in the last slide here. Okay, and with these, it turns out that both the equations end up being one single equation. This is, again, I should have written it in red, marked them as an exercise, but it is an exercise. So if you simplify both the geodesic equations, once you know the Christoffel symbols, it will turn out there's only one equation, namely this one. Okay, there's no two equations to solve, and that's understandable because there's only one function involved, r of t. There's no two functions. Okay, because once you assume it's radial, then you're done, because you really want the radial lines to be geodesics. Why? Because the radial lines under psi will be the great circles, and you kind of know that the great circles are the geodesics. So we are, in a sense, working backwards, having more information. But you could have done this without knowing great circles at geodesics, just by solving for r. Okay, so so this is the only single equation that you have to solve in order to prove that this curve over here is a geodesic. Okay, so how do you solve this equation? Do you do some asymptotics, or do you just solve it? Well, if you think about it for a little while, you'll see that this is something you might have seen, and probably, at least it took me a little while to figure out. But if I were in, let's say, 11th or 12th standard, perhaps I would have done it quicker than as of now, because this is simply solved by putting r of t is tan t. Okay, and you simply calculate, and it will turn out that tan t is a solution. And for those of you who did attend this class on R2 with this metric not being complete and so on, we did solve for this, and we did derive this perhaps in a slightly different way. So tan of t times cosine theta, tan of t times sine theta, this is a straight line passing through the origin, but the parameterization is slightly different than the typical straight line, and this is a geodesic in this metric. This is what we had proved in class, and that's the same thing we are checking now. Okay, so if you apply the inverse of the stereographic projection, what would that happen? That would simply be applying psi to this tan of t cosine theta, tan of t sine theta, right? But applying psi would simply end up being this, because of how the map psi is defined. Okay, but you see, this actually should look familiar. You should remind yourselves of the various trigonometric identities, namely the first two that you learn. The first identity that you learn is 2 sine t cosine t is sine 2t, and this is cosine 2t. So this simplifies to sine 2t cosine theta, sine 2t sine theta, and cosine 2t. And again, this should also look familiar, because this is precisely the equation of a curve lying on a circle, correct? Because this is saying you fix the theta, otherwise this is just sine 2t and cosine 2t. Okay? So if your theta, for example, was 0, then this would be gone. You get sine 2t 0, cosine 2t. So it is a circle. It's part of a circle. Okay. So the theta only tells you which great circle emanating at 0, 0, 1. That's all. So it is a great circle, and that's it. Because any geodesic on the plane is characterized any geodesic with these initial conditions is characterized by this. Applying psi, we get this. And that's it.
Sir, the audio dropped again.
Where?
Sir, you had obtained this cos 2 theta sine 2t, that formula.
Huh.
Till that you had obtained. Beyond that, the few seconds.
Okay, so is this fine? Can I start from here?
Yes, sir.
Did anybody else have other questions or issues? Okay, so what I'm saying is if you literally take tan t cosine theta, tan t sine theta, apply psi, because psi is going to land us inside S2, you're going to get this. Okay,
Yes, sir. That was
remember
okay.
the trigonometric identities. This will simply become sine of 2t cosine theta, sine of 2t sine theta, and the last one is cosine 2t. Okay? So now what I'm saying is this. For those who have played around with stereographic projections and spheres, I mean this is also familiar because this is simply a curve lying on a circle. Simplest instance of this is if you fix theta, let's say put theta to be 0, then the second term drops off and this simply looks like sine 2t 0 cosine 2t. So this is the equation of a circle, but the theta is telling you that which circle. It's a great circle and there are lots of great circles initialized at 0, 0, 1. But the theta is telling you which one to pick. But once you pick that direction, it is a great circle lying on that plane. Okay? In the plane intersecting the sphere at angle theta. So that's it. So the geodesics on the sphere are given by great circles. So the exponential map is now going to be, you should take a geodesic in this direction cosine theta sine theta and then evaluate it at time 1. Okay. So that's the exponential map, right? So evaluating at time 1 should mean that you, so given this direction, so if you take unit vectors at the tangent space 0, 0, 1 of S2, any unit vector is prescribed by cosine theta sine theta 0, correct? Because any vector in the tangent space of T0, 0, 1 S2 has to be a vector which is perpendicular to 0, 0, 1. But any vector which is perpendicular to 0, 0, 1 has to be of the form alpha, beta, 0. But any unit vector now has to be of the form cosine theta sine theta 0. So given any unit vector, this is the exponential map when you plug in t equal to 1. So the exponential map applied to a vector cosine theta sine theta 0 is going to land you into cosine theta sine 2, sine theta sine 2, cosine 2. Because the exponential map is evaluation at t equal to 1. Okay. So that's it. And for general vectors, you can do the same thing because there's a scaling involved and so on, but you can work it out. If it was r cosine theta, r sine theta, some things will change, but you can work out what the corresponding thing is. I just did it for a unit vector. Okay. So I didn't do the last bit, but the last bit is basically once you know what a geodesic is, what all the geodesics are rather, then you know the exponential map, because the exponential map is evaluating the unique geodesic initialized at point 001 with velocity v at time t equal to 1. So that's the map. Okay. So I hope this is good enough for you to be able to write down the exponential map explicitly. Okay. Just try it. If you get stuck, we can maybe discuss it during the office hours at some point next week. Okay. All right. So any questions on this? Okay, so let's see. So I guess there's a remark that I want to make. Just a second. Okay. So we can use rotations to compute the geodesics at any point, and this is a remark that I'm making because we have talked about isometries in class, and remember rotations were isometries. So isometries also preserve geodesics, and this is something we proved last time, or we talked about it last time rather. It's still an exercise. So if you take a geodesic, apply a rotation, that is also a geodesic, which means if I know that geodesics at emanating at 001, I know the geodesics at any other point by rotating, but a rotation map circles to circles. So all the geodesics on the spheres are going to be great circles. Okay, that's the point. And that's it. So because the rotation acts transitively on S2, you can determine the geodesics at any point by the geodesics at a point. And in this case, we just did it for 001, right? So, okay. So the last question, I guess there's nothing much there. Okay, so I'll move on to the last question. So there was a typo in the homework, and so this typo has now been corrected to the plus sign. Okay, so this, I think in the homework it was a minus, but it should be a plus. Actually, uh, for proving that the first part, that this is a smooth vector field, the sign is not too important, but for proving the second part, the sign is actually important. Otherwise, things will not work. So the question is, you define an operation nabla. So you're trying to define a connection. Okay, first of all, you try to define it by defining this connection implicitly by saying you want to define nabla x of y, but you define it by defining it with the inner product with any vector field z. And you define it using this 6-term relation, 6 plus 1, 7-term relation. Okay, this is called the Koszul formula or the Koszul rule. So the first three involves the Riemannian metric. The last three involves the Riemannian metric and the Lie bracket. So note that the Riemannian metric and the Lie bracket, they are all smooth operations. So the right hand side is evidently a smooth function of x, y, and z, because x, y, and z are smooth vector fields, right? And even here you have the inner product, and z is smooth and the inner product is smooth, and the inner product is invertible. It's non-degenerate, in particular it's invertible. So that actually tells you, if you can solve, if you know this for all possible z's, then you know the value of this, because you can evaluate this simply at a basis. So that's essentially the reason why this is smooth. Okay, why this is smooth, and also partly the reason why this is a vector field, because the calculations work out. But smoothness of this is essentially due to this fact that the right hand side is smooth, the left hand side is inner product with z, but this is a smooth and the metric is invertible, so that determines nabla xy uniquely, and it's smooth because everything else is smooth. But yeah, so the first question says show that this is a smooth vector field. So what I gave you is a heuristic. You can make that precise, but let us make that precise by simply work out the formalities. Okay? So as I said, since the metric is non-degenerate, restricted to each tangent space, and you're free to choose z, it's determined at a point by evaluating this vector. If you want to evaluate it at a point, you can evaluate that at a point by evaluating this with respect to a basis z1, z2, zn at the point tpm, right? So at the point p, you have tpm, choose a basis z1, z2, zn, and then if you can evaluate this, that determines this quantity, but that can be now evaluated using the right hand side. So there's a small claim here. We are assuming that we do have a collection of vector fields z1, z2, zn that form a basis of tpm, because I am not interested in a vector, in a collection of vectors z1, z2, zn. I want vector fields. Otherwise, Lie bracket and all these things don't make sense. So we did actually talk about this construction in the class once. So if I wanted to construct local vector fields in a chart, I can always do that. I mean do it, right? So just choose a chart. You have coordinates d by dx, x1, x1 up to xn. There are vector fields which are d by dx1, d by dx2 up to d by dxn. This will be a basis of tqm for all q in u, where u is the chart, right? But these are local vector fields. So what I could do is I could use a bump function and multiply the bump function with either of the vector fields, cut it off inside u so that it becomes a globally defined vector field, smooth. But inside u, it looks like an extension of d by dx1, d by dx2, d by dx. Okay? But d by dxi was a basis. So these vector fields z1, z2, zn will be a basis in a perhaps smaller neighborhood around p. And it's going to be zero outside, but I don't care. The point is there are these vector fields z1, z2, zn, which is going to be a basis for a smaller neighborhood. Okay. So I mean, this was discussed, and again, some of the things I'm repeating for the sake of some students who might have sort of not brushed up on the older material or forgotten. But this is again an exercise that you show that such a collection of Zi exists, meaning that there exists a neighborhood U of P and vector fields Z1, Z2, Zn. These are global vector fields such that Z1, Z2, Zn form a basis for the tangent space TQM for any point in U. Okay. So is that fine? So this is simply choosing a chart, choosing local coordinates, choosing local vector fields, multiplying with bump functions to make them global. But then you have to shrink your u to a smaller set u prime so that it still looks like d by dx. Okay? Because the bump function is going to be 1 on a smaller set and 0 outside u. So the v is going to be wherever it's sort of 1, the open set where it's 1. Okay? So you remove the boundary. So it's going to be 1 on a closed set, v bar. Look at the interior of v bar. All right, so such a thing exists, okay? So the right-hand side is a smooth function, as we just discussed. The Lie bracket Riemannian metric are smooth. And if you write this in this form, fi zi restricted to ui, then you can simply calculate, right? So if you calculate it, so pretend that this was, you can write this as summation fi zi, because zi's are now vector fields which are global but restricted to u. They form a basis at any point. So any vector field restricted to u can be written as functional linear combinations of the basis vector fields z1, z2, zn. So now if I, in the Kojoule formula, in here, if I put zj and take the inner product, what do I get? So remember, fi's are going to come out. I'm going to get inner product z1, zj, dot, 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 fn, zn, zj. Okay, because this fn, zn summed all the way up to f1, z1, this is precisely my gradient. Right? So I just call them xij. Okay, so 2 xij. So the 2 is there because I'm calculating 2 times zj times this quantity, and this is a sum. Okay, and remember this xij is a smooth function because the xij is on the right hand side given by 6 terms. Each of them are smooth. Okay. It's a smooth function of u, and now as j varies, we obtain the matrix. So remember, this is saying that you have the functions f1, f2, fn, and these are the entries of the matrix, right? z1, zj, inner product up to zn, zj. But this matrix is invertible because zi is form of basis. This is invertible on all of u. Okay. So this is simply inner product z1, z1, inner product z1, z2 all the way. That's the first row and so on. So this is invertible, which means you can solve for the fi's as a inverse times xi. Correct? This is simply this. Xi's are smooth functions because of the right hand 6 terms. The matrix A is invertible, so you can solve for the fi's as A inverse times xi, since A is smooth. Everything A inverse is smooth, so the fi's are smooth functions, right? And that's it. So that's takes care of the fact that this is a smooth vector field because this is a smooth function times smooth basis locally, but smoothness is a local property anyway. So that takes care of the fact that it is smooth on u, and since u was arbitrary, this is smooth on all of them. So I just pause here for a moment. Are there any questions that people have on this? So this is a slightly more formal way of saying that you really get a smooth function rather than saying, but the argument really comes from the fact that the metric is invertible and so on. So you just formalize that. Okay? I hope people people followed whatever I said. Okay, so shall I move on? Okay. All right. So the second part, which I mean, this is essentially a computation, and I put everything on the slides because some people who are not attending might want to go back and read the slides and read them at their own time. But this is simply a computation. There's nothing conceptual which is going on here because even Kozul's formula is a bit mysterious and computational to me. So, and I want to rectify that by sort of introducing to you another approach. But anyway, so what do you have to check? You have to check that it's linear in C infinity M linear in X, and it satisfies the Leibniz rule in Y. So these are the two properties that a connection must satisfy. And once you verify this, this shows that the operation nabla xy defined implicitly via this Kojoule formula is actually a connection, right? So you fix vector fields X and Y. So what do you have to show? For the first property, you have to show that nabla fxy is f nabla xy, but remember the metric is invertible. So if I can show this equality for all z, then I'm done. Because then I'll just put z equal to zi, a basis, and then a vector is determined by its inner product with the basis vectors, right? So that's all. So I'm going to instead prove this, and the reason why I'm proving this is because I know the right hand side of each of the two things, right? The inner product of z with something, I know what it is. It has these 6 terms. So let's write it out, okay? So it suffices to prove this for any z. So remember that. So what are the terms? So whenever you look at this Cauchy formula, let me go back here one second. So this is the Cauchy formula, right? This one. So what you're trying to show here is if you insert f here in front of x, the f pulls out, right? But that means what? So that means if you put f here, what happens? Here you get f. So that f is already outside. You can pull it out because it's fx of something. So that f is already outside. Now what about just a second? There was one other term where it wasn't. So fine. So for C infinity m linearity in the x variable, if you put f here, this is the term which is nice. The other terms will contribute something else down the line. But remember, this is also nice. If you put f here, so you'll be putting f in front of x's everywhere. This one is good. This one, well, you don't know because it's z inner product fx, but then there's a y acting on that. Similarly, this is not quite that good. Same with here. But this one is nice because if you put f here, this f comes out because the inner product is bilinear, right? Point-wise. So it's infinity m sort of linear in each of the coordinates. So you can pull the f out. So these two terms are nice for C infinity m linearity in x. The other 4 terms are not so nice. So let's see what's going on. Okay. So that's, yeah. So that's what we started off with. Okay. So these two terms are clearly C infinity m linear in x because the function f pulls out. So what about the other 4 terms? Well, there is this term, Lie bracket fxy inner product z. Well, that, remember what happens when you do Lie bracket fx with y, f is going to come out and then the other one is going to be y of f times x, and you have to take inner product of that with z. This is just how Lie bracket of 2 vector fields work. Okay. So this is simply going to become this, right? F, the term that you want. So this is the term that you want, and this is the term that you do not want. And you hope that this will cancel with something down the line. What about the next term? Well, you also have this term, remember? So what does this term do? Well, this is inner product z with fx. Even here, there's some sort of a Leibniz rule. Either the f pulls out or you get y of f, but this comes with a plus sign. So these two, when you add them up, so you're really adding this term with this term, okay? But then these two add up, so they cancel. So that's good. You similarly hope to have the 2 other, remember there are 6 terms. These 2 terms were nice. These 2 terms combined to be nice because these odd things cancel. The other 2 you expect the same phenomena, that you expect the other 2 terms when you add them, the odd terms cancel and everything is C infinity m linear. So anyway, so what we conclude so far is that this quantity is C infinity m linear in x because of what we just did. But now you can simply interchange y and z because there's nothing specific about, you can interchange y and z and this will still be C infinity m linear in x, correct? Entirely symmetric. So that gives you what? That gives you this is C infinity m linear, and then we are done. Because now, what do we get? Okay. So now if you combine the 6 terms, you see that things cancel out and it's a combination of 6 terms. 2 terms are individually C infinity m linear. The other 4 combine them in blocks of 2 and they are C infinity m linear. So the whole thing is C infinity m linear in the variable x. Okay. So clear? Again, this is something which if you just go back and do it, it will be much more clearer than me trying to sort of, like dig deep and take you through a whole like bunch of formulas, because it's simply a bookkeeping thing that you have to write down and check the signs and everything. Okay. All right. So Yes. So does somebody have any remark to say? Okay. So for the second part, just a second. Some of the line, some line came here. I don't know how, but anyway, let's move on. Okay. So for the second part, we expand this quantity. So what we want it to be satisfying the Leibniz rule in y, right? Which means you simply expand this using the Leibniz rule itself. What does the Leibniz rule say? Sorry, what does the Kojoule formula say? It says that you have these three terms using the inner product. The f comes in front of y, and then you have these three terms involving the Lie bracket and the inner product. And these three terms, I have color coded them in this following way simply because these two terms which are color coded black are already terms where the f comes out, correct? This is what we saw in the x variable. The other four terms are not terms where the f comes out naturally. So the question is, how would those things expand? So this is the usual Kojoule formula. We haven't done anything, but now let's expand. So for the purple one, if you expand, you get x of f, this yz plus fxyz. So this is the function f times the covariant derivative or the directional derivative of the inner product yz along the direction of the vector field x. So this is just the Leibniz rule. Okay? Similarly, the black term is already there because its f is already outside, so that's fine. What about the red term? The red term is going to be similar, right? It's either the f comes out and it's z acting on inner product xy, or z acts on f. This is a function, and then you have inner product xy, right? The next term, well, that's the same thing as this term here, and that is already C infinity m linear, so I can pull the f out, which is what I just did. What about the blue term? Well, the blue term will have two terms, same reasoning. And the green term will also have two terms, same reasoning, right? Okay, so now if you look just a little closely, so all of you are staring at the screen, perhaps. So if you look closely, you see that certain things will cancel. So what cancels? Remember, this cancels, right? These two, because inner product is symmetric. So xy is the same as yx, and this comes with a minus, this comes with a plus, so that's 0. What else cancels? Any cancellations? Well, you see that this term over here and this term over here, it actually adds up. It doesn't cancel. So you might be alarmed at this point if you haven't really thought about this a little bit. But there's nothing to be scared about. The point is, we are not trying to show that this is C infinity m linear. We're trying to show that it satisfies the Leibniz rule. So you do expect a term of the form x of f, and then the usual C infinity m linear term. That's what the Leibniz rule tells you. So, and since there's a 2 here, you do expect that to happen. So let's now simplify, right? So the green term and the purple term, they combine to give you 2x fyz. What about the other terms? Well, the other, so I mean, these two cancel. So whatever you're left with are these 6 terms, right? 1, 2, 3, 4, 5, 6. But these 6 terms are precisely this. The f comes out in all of these 6 terms, okay? You can, if you pull out the f, what you're left with is precisely 2 inner product z with nabla xy. That's again by the Kojoule formula. Okay. But that's it. But then you're done, right? Because then that precisely says that I can now put the xf back in here. And because this is true for all z, and the inner product is non-degenerate, I'm obtaining that this quantity is nothing but xf into y plus f nabla xy, just by the non-degeneracy of the metric. Okay. So that's it. So is that clear? Okay. All right. So let me move on then, in case there are no questions. So Just a second, I'll just see there was some chat. Okay. So did somebody write something in the chat? All right. Anyway, so let's move on. So there are two questions left. The last one, yes.
That was a way ago.
Huh?
So that I wrote, but that was a way ago when your voice went.
Okay. Fine. All right. So now I think it's okay, right?
Yes.
Okay. So there are two more questions left. So this one. Okay. So this one ideally I wanted to do because I like these kind of questions. This is perhaps a little too intricate for an exam. Okay. However, if you do care about Riemannian geometry and conformal change of Riemannian metrics and so on, and like conformality is a very key concept to understand in geometry, complex analysis, scalar geometry, all over in mathematics. So this is something related to that. So that's why I wanted to give this question. The question would have been hard if I just said show, or if I just said compute the Levi-Civita connection with respect to this metric. Okay, so the notation here is as follows: that whenever I have a metric G, I'll use nabla superscript G to denote the Levi-Civita connection for the Riemannian metric G. Okay, so this thing here means this is the Levi-Civita connection with respect to the Riemannian metric G. The X, Y are as usual, and this thing here means this is the Levi-Civita connection of the Riemannian metric G times e raised to 2 phi. So why is e raised to 2 phi? Well, G times e raised to 2 phi, phi is just any function. So if you look at the new metric looks like the old metric pointwise times scaled by e raised to 2 phi at the point P. So e raised to 2 phi P is going to be some positive scalar. So you're simply rescaling the metric at every point. But the rescaling factor may not be constant. It is just some positive constant, but the positive constant changes smoothly as your point changes in it. So that basically means that the lengths of your tangent vectors might change in the new metric. The angles between them do not change, right? Because the dot product rule is given by, you take the dot product of two vectors and then you divide by the length, that's the cosine of the angle between them. So that doesn't change. So that's the notion of conformality, that it preserves angles. Okay? So this Riemannian, the new Riemannian metric also will have the same angles as the earlier metric. The lengths will of course get changed. So if you read these kind of things later on, this is simply saying that you start with the Riemannian metric and then you're choosing another Riemannian metric in the same conformal class. In any case, so the question is about comparing the Levi-Civita connection of one with respect to the other. And that's sort of where this question becomes interesting and important. But for us at this point, since you're given what to compute and what to prove, it rather becomes an exercise in checking things. So, but the context is there, okay? So it says that this new Levi-Civita connection looks like the old one, plus there's a term, the whole thing is symmetric in x and y because it's directional derivative of phi in the direction of x times y, and then you switch x and y. And then there's this term, which is the inner product of x, y in the G metric times gradient phi. And there's a remark here, which I'll get to in a moment. Okay? So to define the gradient of a function, you need to have a Riemannian metric. You cannot define the gradient of a function in general. So the confusion that some of you may have, if none of you have this, then I would be really happy. The confusion that some of you may have is on our end. You do not need any Riemannian metric. If you are given a function, the gradient is simply whatever you call grad, right? So it's d by dx1 f dot dot d by dxn f. The problem with that is in Rn you have this global canonical coordinate, so to speak, and you just define grad that way. On a manifold, you do not have global coordinates. You do have local coordinates, but then when you have local coordinates, you might choose a local coordinate system xi's and define the gradient to be d by dxi of f. Someone else might choose the local coordinates to be yi's and define the gradient to be d by dyi's of f, and they may not agree, right? So how do you fix this? Well, one way to fix this is through a Riemannian metric, or essentially the only way practically to fix this is through a Riemannian metric, or by choosing an orthonormal basis del by del x1 up to del by del xn, and then defining the gradient to be the usual gradient with respect to this del by del xi. But to declare them to be orthonormal, you need a metric. So that's a whole point. Okay? Anyway, so yeah, so to like get to the point, the gradient of a smooth function on a Riemannian manifold is defined implicitly by this identity. Okay, what is this identity? This is saying whatever this gradient f is, it should be a vector field, and you determine that vector field by evaluating that by pairing this with another vector field x. So this is now going to be a smooth function, and you want this smooth function to be nothing but the one form df acting on the vector field f. Remember, f is a smooth function, so df is a one form, and df acting on a vector field is a function. So you're defining it implicitly, because you're not saying what this is as a vector field. You're using the fact that this inner product is non-degenerate, like we have been using in the last two questions, to define this implicitly, but it's still well defined because you can solve it locally, uniquely, and so on. So this is the definition of gradient of f. It's defined to be that vector field which, when paired with any vector field, is nothing but the one form df acting on the vector field you're pairing with. But this requires this inner product. At least it requires a non-degenerate inner product. Okay. So the grad that you see up here, this is the gradient with respect to the metric g. This is not the gradient with respect to the new metric. So just keep that in mind. This is gradient phi with respect to this metric. Okay. So any confusion or questions regarding this notion of gradient? Okay. So there are two ways to check this. Okay. So what are the two ways to check this? So this exercise in red basically means that you prove this formula, but you prove this formula by simply using the Koszul formula for this with respect to this metric, and using the Koszul formula for this with respect to the G metric. And then you simply go by the fact that the new metric is nothing but the scale version of the original metric. So you can prove that. This is going to be purely computational proof using Koszul formula, which is still mysterious, but it's probably going to be half a page, but you can prove it entirely by using Koszul formula on both sides. Okay. So that's one way to prove it. So essentially, you're still using the fact that the Koszul formula defines this unique metric compatible and torsion free connection implicitly, because that's what we use to prove the fundamental theorem. But the point being, you're using the Levi-Civita connection implicitly, but using the Koszul formula explicitly. Okay. So yeah, just give me a moment. Okay, so all right, so again, I'll leave it to you as an exercise, and maybe in the next tutorial session, whenever that is, maybe next month, I'll not prove this, but I'll expect some of you would at least go back and try to prove this by this method. We'll take a different method. Remember what we want. We want to compute the Levi-Civita connection of a metric in terms of some other things. But we know that Levi-Civita connection is unique. So it would suffice for us to show that this right-hand side is metric compatible, condition 1, and this is torsion free, condition 2. So if you can show that the right-hand side satisfies both those properties, we're done, because then that would be the Levi-Civita connection for this metric, the conformal metric G to the 2 phi, the metric conformal to G. All right. So that's the approach that we'll take. We'll use the fundamental theorem of Riemannian geometry, and we'll turn it around by saying that we can use that to deduce what we want, provided we check for the two conditions which guarantees the fundamental theorem. All right, so so I guess, so some participant dropped off, I guess. Okay, anyway, it's fine. Okay, so let's just, so again, I'll leave this to you to check, but so you have to, of course, first of all, check that the right-hand side indeed defines a connection. Okay, only then can you resort to the fundamental theorem. So the right-hand side defines a connection means what? That it defines a vector field. Well, it's clear that the right hand side is a vector field because everything is a vector field. You have to show that the right hand side is C infinity M linear in X, and it satisfies Leibniz rule in Y. Correct? So that's something, it's very routine. You can go back and check it at your leisure. So I'll not spend time on that. It can also be verified that this is torsion free. Why? Well, simply because of how things are, right? So what is the meaning of torsion free? It means you calculate nabla x, y with respect to this metric. You subtract nabla y, x, and then you hope that to be the Lie bracket x, y. But remember, if you interchange x, y here, this term cancels and subtract. These also cancel. What you're left with is nabla xy minus nabla yx, but that is Lie bracket xy because this is the Levi-Cevira connection. So this is torsion free. There's almost nothing to check. Okay. Okay. So the main thing is metric compatible. So how do you check it's metric compatible? Well, you just use. So metric compatible means what? It means you calculate two terms. One of them is of the form nabla x y inner product z. Other one is y inner product nabla x z. And then this should actually equal x inner product yz. But I'm writing the metric as a subscript because there are two matrices, when there are two metrics floating around. So this is what I want. But what is this quantity? Remember, this metric is nothing but e to the 2 phi times whatever you would get by the usual g. Correct? Okay. But if you do the usual g, what do you get? You basically, now if you see that if you calculate this quantity, this is simply going to be so let's write it out. So this is going to be nabla x g to the 2 phi y inner product z. Okay. And if you expand out this formula, so you know what was given to you, right? So you're given 4 terms. So I'm going to simply apply those 4 terms back here. So here you get e to the 2 phi, that is a scaling, times these 4 terms, correct? So this is e to the 2 phi into the first 2, this is e to the 2 phi into the last 2. And then your inner product with z, but these are inner product with respect to the metric g because they have pulled out the e to the 2 phi. Is the first line clear? If it is clear, then the other ones are going to be equally easy. Okay? So this is simply plugging in the formula and then applying the inner product, but now the inner product is happening with g because they have pulled out a 2 phi. So this simply means the usual bracket with g, but the 2 phi comes up in front. What about the next term? It's the same thing, right? And I've color coded these with red and green because then it's pretty clear to you which ones will be adding with the opposite sign so that they cancel. So now if I add these two terms, what should I get? The red ones cancel, the green ones cancel, the black ones add up as they should be. And what do I get? Well, if I sum them, this is what I get, right? So if I sum them, the reds cancel, the greens cancel. So you get nabla x, y, z, nabla y inner product, nabla x, z, and you have two of the same terms. So this is what I get, correct? Okay. Okay. So what is x of fg? Remember, what I get is this term. What is x of e to the 2 phi? Well, x of e to the 2 phi is going to be, this is just by, this is like e to the phi into e to the phi, this product rule or Leibniz rule if you wish. So you'll get e to the 2 phi into 2 times x of phi. Okay. So if you replace this out, just a second. Why did I say this? There's something that I missed. Okay. Yeah. So remember, metric compatibility means what? I missed a line here, so I apologize for that. So what you have to check here is that this quantity, metric compatible, means it should be the inner product of yz with respect to the metric g e to the 2 phi, and then that function differentiated with respect to x. And I'm saying that is actually this quantity. Why? Because inner product yz with respect to g to the 2 phi is nothing but inner product of yz with respect to the g metric times e to the 2 phi. But then when I apply x, what I get is either e to the 2 phi comes out, or I have to apply x to e to the 2 phi. And if you do it correctly, which I missed a line and you should probably go back and redo it. You obtain the desired equality. So metric compatibility means differentiating the inner product of yz along x is nothing but the sum of these two terms. So that's a line that I missed. I'm sorry, you should just fill it in. Okay. So modulo that, are there any questions on this? So this is perhaps a slightly smaller calculation than using the Kojoule rule, but Kojoule rule will work provided you're fine with a large number of terms and see things will simply cancel. But we are using the version of the Kojoule rule, which is the fundamental theorem. So at both instances, we are resorting to fundamental theorem one way or another. Okay, so let me move on to the next question. So this is the last question that we'll talk about, and then we'll stop. Okay. So this one is something we did talk about in class, and actually I had assigned part of this as an exercise. I don't know how many people went back and did it, but this is something very nice. Actually, this is something you might have seen in calculus of several variables on S2, for example. So the question says you have two smooth vector fields on Rn plus 1. You restrict to vector fields on Sn. So in other words, you might pretend that these are vector fields on the sphere and you are extending them to Rn plus 1, but here we're doing the opposite. So you simply want to calculate the Levi-Cavita connection on Sn with the round metric. Remember, we talked about the round metric. This is nothing but the induced metric from Rn plus 1. So the Levi-Cavita connection for the round sphere, meaning sphere with the round metric, is given by this formula. Okay. So this, remember, is dy. So if y is a vector field, dy is going to be a matrix, and this matrix acts on a vector that's going to give you a vector. This is at p, and then this is a linear product, that's a function multiplied by p, that is also a vector. So the right hand side is indeed a vector. Whether it's a tangent vector at p or not, that's something which is not clear from the formula. Remember, for this to be a connection on Sn, at the point P, this should be a tangent vector at P. So even to begin your analysis, you have to first show that this is a tangent vector at P, which means you have to show that this dotted with P should be 0, correct? But there's already a P factor here, and P dot P is 1, which means you have to show something very precise, okay? But once you show that it's a tangent vector, the rest of the things would fall out pretty easy. So let's see. So hopefully it's clear. So Levi-Cavita means you have to show that it's metric compatible, it's torsion free, and it's a connection. So connection meaning it's the infinity M linear in X, satisfies the Leibniz rule in Y. Okay. But here, as we pointed out, even before you begin all of this, you have to show that this is actually a tangent vector at the point P. So let's start. So let's take an integral curve gamma initialized at P, and this is an integral curve for the vector field X. So the vector field X is a global vector field on Rn plus 1, but you restrict that to Sn, you get a vector field on Sn, and you choose an integral curve for X initialized at P. Okay. So then if you look at this function, look at y of gamma t. Y of gamma t is a tangent vector at the point gamma t, but it's a tangent vector at the point gamma t on the sphere. So this being a tangent vector, by the very property of tangent vectors being perpendicular to the points on sphere, this is 0, identically 0, correct? Because this is a tangent vector t gamma t of Sn. This is the point gamma t, so the dot product is 0. Right? So when you see an equation of this form, something is 0, we know what to do. You either integrate or differentiate. Well, integration doesn't really give you anything. Differentiating something like this always gives you something nice. So if you differentiate, what do you get? You're really, yeah, so there's a typo here. Okay, so this t should come down. This is d at gamma t. So if you differentiate this, this is simply linearizing this map y, so that would be dy at the point gamma t acting on, so yeah, so this x is actually bad. Okay. So what should happen? So I mean, this is basically, so it's you have to use the product rule first. It's going to be the derivative of this dotted with this plus this dotted with the derivative of this, correct? Now, what is the derivative of this? This is where you have to use the chain rule. This is going to be dy at the point gamma t acting on gamma prime t. But gamma prime t is x, or x of t, because gamma was an integral curve for x, right? So that's why this thing appears. This t is going to go down. This is d of y at the point gamma t acting on x. So that's a vector dotted with the vector gamma t. The rest is y of gamma t dotted with y prime t. So this is 0 because it's the derivative of the constant 0 function. Now, when you plug in t equal to 0, what do you get? When you plug in t equal to 0, this is d of y at gamma 0, which is dp. This is simply x. This becomes p. And what about this quantity? This is y at gamma 0, that is y of t, dotted with gamma prime at 0, but that is x at t, right? So that's it. But I can move this term to the other side. What I get is minus. Or I can keep it the same way. So the point is, if you dot product dy acting on x at p with p, you simply get this term back, right? So what does this tell us? It's telling you that I simply look at this quantity, right? Remember, this is the usual covariant derivative of y in the direction of x. This is how we define directional derivative of vector fields in Rn, and this was discussed at length in the class. So this is the usual Levi-Civita connection on Rn with the usual metric, Euclidean metric. What we saw in class is that the Levi-Civita connection on a manifold induces a Levi-Civita connection on a submanifold by projecting the connection component onto the tangent space. This is a theorem which we had proved. You can go back and look at it. So we could have applied that also. Okay? But in particular, what we're deducing here is that this vector here, okay, is indeed 0. Why? Because once you have this, if you dot product this with, so this is precisely telling you that, right? If you dot product this quantity with p, this becomes 1 because p dot p is 1, and then you get this plus this, but that is 0 because of what we just deduced. So this is indeed a tangent vector at the right point on the sphere, first of all. This is actually telling you more. This is telling you take the usual covariant derivative, dot product with p. But dot product with p simply means that you're removing the normal component, right? So this dy at x, so dy acting on x will have two components, the normal component at p and the tangential component at p. But the normal component at p is some multiple of p, and it's saying it's this multiple. Right? So to project it onto the tangent space, you have to subtract off that, which is minus of minus. So that's why you're adding this normal component, so that this now lives in the tangent space. That's precisely what we proved now. So this vector has a normal component, and when you subtract off the normal component, what you get is the tangential component. So this is an element of Tp of Sn. Okay, so it is indeed a vector field on Sn. So now it's routine. So you have to show that it's torsion free. But why is it torsion free? Well, because you see, when you subtract off, when you take nabla xy minus nabla yx, this term is symmetric, so this cancels. What you're left with is dyx minus dxy, but that is torsion free because this comes from the Levi-Civita connection on Rn plus 1. So this is true. Why is it metric compatible? Well, you simply write it down. What is this going to be? This is going to be this again, because any vector z, which is a tangent vector, when you dot with p is 0. And remember, this one has two terms. One of them looks like this, and the other one is some scalar times p. But p dot z is 0. That's why that term doesn't appear. But then this is this simply because this was the original Levi-Civita connection on Rn. So it is metric compatible as well, for same reason. So the extra term cancels out, but you do need the extra term, the normal direction, because that is precisely minus of the normal component of the usual covariant derivative or Levi-Civita connection on Rn plus 1, and you're simply removing that normal component to get a Levi-Civita connection on the submanifold. So it's an instance of the general theorem that we have talked about. Okay. So let me just end with one remark here. So the remark is that we can solve for geodesics in the round metric using this Levi-Civita connection. Remember, we solved it first of all using exponential map and actually calculating geodesics for S2, but you can do the same for Sn. Well, how do we do it here? Well, remember for Levi-Civita connection, geodesics can also be defined by this equation, because the Christoffel symbols for the connection and the geodesics are one and the same. So what would this mean? This would mean that, remember this quantity, if you go by our formula, this quantity is simply going to be an acceleration which is orthogonal to the tangent space, simply because whatever the derivation is, if you differentiate along gamma prime, that's simply going to be gamma double prime. But when you project it to the tangent space, that should be 0. Because this is precisely what this is, right? It's the usual covariant derivative of gamma prime along gamma prime projected onto the tangent space, and that should be 0, which means the acceleration should be perpendicular to the tangent space. And this is again an instance of the special case that we saw of a surface in R3. So this kind of ties everything together. Okay? In fact, in this case, if you go through the actual equation, we'll see that we'll have to solve this equation. If you write down the formula for nabla xy that we had, the equation is this. But this now goes all the way back to high school. This is an equation that all of you know how to solve. This is something to do with circles, right? Cosine t and sine t. And that's it. So these are great circles. So no surprise, we get the same thing through a different approach. So are there any questions about this whole thing, or any other remarks that you have regarding the setup? Okay, so if not, then okay, so I just stop here.